Hey there, this is Verbsky, lecture over variation of data, unit 6B. Well, I'm going to keep it pretty cookie cutter. Let's say we have a set of data in descending order, and we're going to have 11 pieces of data, and I'll stop writing here in a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, what we're going to do is we're going to define some terms here, and we're going to work from there. What we're going to do first is find the middle of our data set. If there's 11 terms, there's a set of 6, 1, 2, 3, 4, 5, 6. Oops, that would be, excuse me, a set of 5 terms, and another set of 5 terms with a very distinct middle number, which is 9. This is the second quarter, Q sub 2. Second quarter, 50 percentile mark. And you guys also know it's called the median. Medium. Now, you knew that from before. You didn't know about the Q2 or the 50 percentile, but it is the median. Now you look at the lower set. This is the lower set. And you find the middle of the lower set, which is easy to do. It's 3. This is called the first quarter, or Q sub 1, and a quarter is worth 25 cents. So we located the 25% marker of the data. And finally, you look at the upper set, and we find the middle of the upper set, and that's the third quarter, the 75 percentile marker. Now, we're also going to find the minimum, and we say min. Clearly, the minimum value is 2. We're going to find the max, and that's 19. These 5 pieces of data, min, max, Q1, Q2, Q3, are called a 5-number summary. And associated with a 5-number summary is a graph. And this graph has a name. It's called a box and whisker. Uh-oh, how do you spell whisker? I'm good in math, but definitely don't know how to spell the word whisker. Box plot. Here we go. WH. You can laugh all you want. Plot. Now, it's kind of a one-dimensional graph, meaning it just goes this way. And you look at my data, and it's running from 2 to 19, so I'll start out here at 0 and go 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. My ticks aren't perfect, but close enough. What you do, anywhere you want, you're going to make a box. Now this box is based on Q1 and Q3. So the box is based on Q1 and Q3. Now the start of the box is at 3, and the end of the box is at 14. So at 1, 2, 3, you just make it. You can make it as fat as you want. You can make a skinny box or a fatter box. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now you got to make a box. Like I say, the fatness doesn't matter. Now inside the box, you mark the median, and that's 9. 4, 5, 6, 7, 8, 9. So you can see there's 6 units here, and there's 5 units here. So this part is bigger than this part, but this is the 25 percentile. This is the 50 percentile. This is the 75 percentile. And now you add the whiskers using the min and the max. So from 2, you just put a whisker right in the center of your box. And the max being 19, 15, 16, 17, 18, 19, whisker to the middle, and then you can see your data spread. Now, this is this is your data spread. So 25% of your data is here, scrunched up in this little thing. The 25 to 50% of the data scrunched up in here. And then this a little smaller. And then the last 25% is spread out here. You kind of know where your data is. It's a visual summary of your data. Box and whisker plots are very, very powerful. If you stack box and whisker on top of box and whisker, you can use them to say things about your data that you normally would not be able to say just by looking at the number set. So they're really good. They're fun to draw. Got a funny name, box and whisker. Remember, make your box with Q1, Q3. Fatness of the box doesn't matter. Throw down your median, put your whiskers in, and you got yourself a box and whisker plot. If you've never done it before, kind of fun. If you've done it before, it's not that bad of a thing. Okay, now let's work with a different data set. Let's work with 12 pieces of data. So this is example 2. At example 1. So 2, 3, 5, 7, 8, 12, 13, ascending order please, 17, 20, 21, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 24, and 30. So you got a set of 1, 2, 3, 4, 5, 6, and another set of 6. The middle of a 6 and 6 is 12.5 because you got to take the average of those. 13 plus 12 divided by 2, or just guess the middle of 12 and 13. It works. So that's the Q2, the second quarter, i.e. the median. Now your lower set is a set of 6. So you got a lower set of that of 3 and an upper set of that of 3, and you got to take the middle of 5 and 7, and that gives you 6, known as Q1, the first quartile, the first quarter. Then, once again, you take your set of 3, you take your set of 3, and you split the middle of 20 and 21, picking up 20.5 to be the third quarter, i.e. quartile 3, with a min of 2 and a max of 30, and then you can draw the corresponding box and whisker plot. I'll draw a pretty bad one here. Let me try. Just freehanded. So if I go 0 and 30, and that's about half, so that's a 15 marker, and this is about half, so about 7.5, and it's 22.5. See, I'm not going to draw 30 ticks here. What I'm going to do is cheat a little bit. I'm going to say this is 6, this is 20.5, with a median of 12.5. Let me see, I'm just guessing this is 12.5. 2's in here, and 30's here, and that's a really bad box and whisker plot. But see how the data's clumped up here, data's kind of clumped up here, data's kind of spread out here, and this data is pretty spread out right there. It's a bad plot, but I can see it. Even though it's bad, it's a great way to just look at data. Now, I normally do even more with this, but this book kind of steps back a little bit. Um, so that's all there is to it. Hey, good for a test. There's a lot of good things like defining outliers, which the book didn't go into. Um, and, I kind of like to if I got time, but for right now, let's just keep pushing ahead. There's a second way to kind of look at your data, and it's called standard deviation. Now, standard deviation is basically a made up distance formula. We have a distance formula, for example, to find the distance between 2 points, like the point 1, 2 and the point 5, 1. There's this distance formula that we just memorize to be, you subtract your x's and you square it, plus you subtract your y's and you square it, and you get 16, 1 square root of 17 is this distance. Now, what standard deviation is kind of like an average distance formula. It finds the distance that each piece of data is away from the mean in a 2D fashion, and then divides by the number of data. But sometimes they divide by the number of data, and sometimes they divide by the number of data minus 1. And that's pretty technical. But we're going to learn the process. I like the process. What I need to do, though, if I'm going to teach this, is come up with a really good problem that has a really good mean or average. So what we're going to go is with 10 numbers. So like 1, 3, 4, 4, 5, 7, 8, 11, 1, 2, 3, 4, 5, 6, 7, 8, 12, mystery number. So far, the first 9, I got 4, 8, 12, 24, 32, 42, 52, plus 3, 55. So I add these up, and I'm at 55. And I'm going to put a 15 in here, making it 70. And then you're going to divide by 10, and you get a mean of 7. So here we go. Got a question for you. What is X bar? That's known as the average, but now it's called the mean. And you go 1 plus 3 plus dot, 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 plus 15 over 10, 70 over 10, 7. Now, before I actually write down the formula, I'm going to just show you what I do. I rate my data vertically, so I just write my xi's down. This is going to take a while. So 1, 3, 4, 4, 5, 7, 8, 11, 12, 15. So you write your data down. Then you go to your data minus your X bar. Just like I did in the formula, I went, subtracted the X's, subtracted the Y's. Now we got to go where this is 7. So we go 1 minus 7, 3 minus 7, 4 minus 7. Remember, it's made up. Just do what they say. And this is what we're doing. Don't ask questions, just do. Trust me, statistics is actually theoretically really challenging. But if you just do what they tell you to do, it's kind of fun. I can follow directions. This is kind of, I'm just subtracting here. 8. Now we're going to square them. Why? Because it's like the distance formula that I did above. After you subtract them, you're supposed to square them. Remember, some statistics god made up this rule, and we just do what they say. So you square these numbers, -6 times -6, 36. 4 times 4, the negatives cancel, 16. -3, double negative 9. 9, 4, 0 times 0. 1 times 1, 4 times 4, 5 times 5, 8 times 8. And what do we do up here? We added them. But here's the pain. We need to add them up. Now, in math, we say this is the summation, meaning add up the xi minus the x bars squared, which just simply means we add those up. And I need to, maybe I can get them all on the page here. Whoopsie daisy. Here we go. There we go. Sixteen plus 9 plus 9 plus 4 plus 0 plus 1 plus 16 plus 25 plus 64. Oops. Plus 64. Ooh, 144. This is a great problem. That number never works out. Now, we take that number, we add them up, and then we divide by total number minus 1. So, since we have 10 pieces of data, we divide by 1 less. We divide by 9. So what we're going to do is take that 144 divided by 9, you get 16. Unreal. This is a perfect problem. I don't think I could ever make this up again. And finally, take the square root of this. And that's what we call the standard deviation. And it's got a fancy name. It's called the average deviation from the mean. And that's why we don't use the word average anymore. We use X bar and we call it mean. Because you don't want to say the average deviation from the average. That wouldn't be good. So standard deviation is average deviation from the mean. Normally, the problems work out pathetically bad. So there's a problem actually in a book, page 391. Book has a problem, and it's got this data 4.1, 5.2, ... 11.0. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pieces of data. So there's 11 pieces of data. Now we know X bar, because they found it, was 7.2. So you go 4.1 minus 7.2, and you get that, you get minus 3.1, and then you square it, and you get 9.61. And the same here, 5.2 minus 7.2 equals negative 2, which is 4 when you square it. Dot, dot, dot. And you get 11 minus 7.2 is 3.8, dot, dot, dot. And then you square it, and you get 14.44. Now they add all these up, 38.46 divided by 10, because we had 11 data, and we get 3.846, and you take the square root of that, and that's the standard deviation, which is, I don't know. Let's see if the book, oh, there we go, 1.96. Standard deviation of 1.96. And then they actually do side by side. They got another problem. And I just wanted to make sure you understand that this process is really ugly sometimes. Now, I didn't do that whole problem. You see how I skipped all this work in here? Then I just looked this up, divided by 10. I did that myself and took the square root, and I looked that up. But what about our calculator? You can go stat, edit, and enter your data. 4.1, 5.2, 5.6, 6.2, 6.7, 7.2, 7.7, 7.7, 7.7, 8.5, 9.3, 3, and 11. That's the problem I just did. I scooch up, see how there's, says there's 12 pieces of data there. I screwed up. So, oh yeah, there's only two 7.7s. So delete one of those out. There's 11. I always check. There's 11. So you get my data in by hitting stat and edit. Now you get out. You go second quit. Now if you go stat, calculation, first variation statistics, this calculator is staring at list 1, and I'm going to just go down to calculate, or you people with the other format, just hit enter. And X bar 7.2, see S sub X on your calculator, this is S sub X. Sigma X is very simple, very similar to SX, but it depends on whether it's a sample of some data or just basically a large data set. It's an actual data set or a sample of a data set. I'm trying to read the problem. Calculate their standard deviations for the waiting times at Big Bank. They don't spell it out. So we are using S sub X in this course, not sigma X, at least right now. So we divide by, and the difference is, one you divide by 11, the other one divide by 10. We're using the standard deviation where you divide by 1 less than the number of data. So if there's 11, you divide by 10. If there's 58, you divide by 57, right there. And then you take the square root. Doing good, we're only at 25 minutes. Finally, the book finishes with this weird thing. The range rule of thumb. And what they say is S sub x, which is standard deviation, is approximately equal to the range divided by 4. And the range is the max minus the min. So going back to my perfect problem, the problem where life was great, I don't think I've ever constructed a better problem in my life. Go find that thing. Yes, the 1, 3, 4, 4, 5, 7, 8, 11, 12, 15. Let me see if I can write that down. 1, 3, 4, 4, 5, 7, 8. 1, 3, 4, 5, 5, 7, 8. I don't think that's right. 1, 3, 4, 4, 5, 7, 8. 4, 4, 5, 7, 8. 11, 12, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got a min of 1 and a max of 15. Therefore, the range, 15 minus 1, which is 14. They say that the standard deviation of my data should be approximately equal to the range divided by 4. So range divided by 4, seems like I should know that. 3.5 probably. 14 divided by 4, 3.5, is approximately equal to the standard deviation, which I got to be 4. Just some fact that somebody came up with that they should be approximately equal. Now, if they're not, if range divided by 4 is not even close to equal S sub x, that means max or min is an outlier, which this book forgot to introduce again. They could have, but they did not. So here's an example. Everybody does crappy on a test, and you got your data set, and you kind of know how it's behaving, except there's that one smart kid. Everybody else got below a 60, and then you got that one person that got a 100. That would screw things up, because that 100 would be an outlier. It's way out there, and it's going to screw up this little relationship that some really smart guy came up with. To be honest, I have never done range divided by 4 is approximately equal to the standard deviation. But I think it's really cool. So they are avoiding outlier. But wait, in the same theorem, they actually finally define it, and it's really weird. So they're almost there. They almost did it anyway. So the min should be approximately equal to x bar minus 2 standard deviations. And the max should be equal to x bar plus 2 standard deviations. Now, this, and they're not saying it, is this and this are basically tell you how to find an outlier. So I like to call it my box of goodness. Here's what I like. This is the interval of goodness. And it is x bar minus 2sx and x bar plus 2sx. Now the book doesn't come out and say this, was really weird. Now in my problem, this perfect problem that I got lucky and created, we know x bar was 7, and we know Sx, the standard deviation, after a while, was 4. So 7 and 4. So here we are, we're trying to talk about outlier at the tail end of the lecture, and you're tired, but 7 minus 2 times 4, and 7 plus 2 times 4. This is the interval of goodness, and I get 7 minus 8 is negative 1, and 7 plus 8 is 15. That is the IOG, or interval of goodness, however you want to talk about it. My data set is 1 to 15. So 1, 3, 4, 4, 5. Okay, here it is. Is my data set, view, zoom, view, zoom. So here's my data set, 1 to 15. But my interval of goodness is negative 1 to 15. X bar plus 2 standard deviations away from the mean. Yep. My data is between, barely, the 15 just makes it, just squeaks in. The 1 made it in no problem. So my interval of goodness says that all my data is good. So my data set is just inside interval of goodness. Therefore, no outliers. So if you would do this and you find your inner goodness, say, to be 14, then 15 is an outlier, and then you wouldn't expect this really cool thing, the range divided by 4, to be approximately equal to Sx. Or once again, if you had that all these low test scores and then that one person gets a 100, the 100 is technically an outlier. And then, you know, what are we going to do with outliers is the next question. So outliers just screws everything up. That can we just get rid of the 100? Everybody got a bad grade, hoping the instructor's going to forget about that 100. Well, anyway, I probably did a little more than I should have, but good enough for now. Thanks for listening. Hopefully it helps you with the problems. Once again, I must say I really, really, really like this section. Thank you.